Our next speaker is Brandon Moak. Brandon co-founded Embark and currently served as Chief Technology Officer. In his role, he leads engineering and R&D at Embark and has overseen development of Embark driver software, the core of Embark's commercialization effort. Brandon also led the design and development of the Embark Universal Interface. Brandon is an experienced engineer and previously worked at Kendra.ai and Clearblue Technologies. Brandon, over to you.
Hi everyone, I'm Brandon Moak, CTO of Embark Trucks, and today I'm going to be talking to you about building a deep learning ecosystem that scales. So a little bit about me. I'm the Chief Technology Officer at Embark Trucks. In my role today, I have roughly two responsibilities. One is building the team and the other is the technology story. But where I started 6 years ago is very hands-on with the technology, everything from writing low-level code to connect motors to computers, all the way through the stack to writing algorithms to do lane detection in images. A little bit about Embark. Embark's mission is to bring the first commercially viable self-driving truck to public roads by building the self-driving software that can power any fleet. And I'm proud to say that Embark is America's longest-running self-driving trucking program. We began on-road testing back in 2016, and I think we've got a really unique approach to the problem that really has two parts. First is the simplified technology problem. When we first set out in self-driving, I think we had a little bit of humility in understanding that the self-driving problem is really, really hard, and you want to do as much as possible to reduce the scope of the effort. The second piece is that it's got a really compelling business case. In America today, there's a massive driver shortage. There's 80,000 jobs open to become a truck driver. The average age of a truck driver is over 50 years old. And all of this is compounded by global supply shortages. And so we believe that trucking is the first place that automated vehicles will come to the public, and it's powered by these two reasons. The high-level architecture of our software can be thought of in roughly 4 parts: sensors, detection and fusion, prediction and planning, and controls. So the sensors, they provide the vehicle with an understanding of what's around it. The detection fusion stack is how we take that sensor data and come up with a real-time understanding of what the world looks like around us in 3 dimensions. Then prediction, planning, and control from there is we interpret this scene, we figure out what's most likely to happen, where should we go, and how do we actually physically control the vehicle to get to that point. Today, I'm going to be diving a little bit deeper into our detection stack and, more importantly, a few of the processes and learnings that we've had over the last 6 years to go from what very much was a startup environment, sort of shooting from the hip, to a much more mature and rigorous program around building deep learning and machine learning models. So a little bit of history of deep learning at Embark. I would say the early days of deep learning was very bootstrapped. We had a lot of labels made in-house by engineers. I personally spent a lot of time drawing lane lines and images and drawing bounding boxes around cars. The applications themselves were very focused, so think like single camera view, single task, right? Just extract the lane lines from this single image. And it was a very controlled operating environment. We knew that 25 miles of road that we wanted to operate on. And we were very successful. We were able to deploy very performant models for these small focused tasks within just weeks. But our ambitions were obviously far greater than just doing these simple tasks, and the challenges quickly grew. We added additional sensors, different field of views, Lidars, and cameras. We started to expand the operating domain, so we drove in multiple states, multiple locations. What became tricky was handling different weather conditions. And we wanted to get a lot more information out of our networks. So starting to detect more than just lane lines, like road surface, construction signs, and everything else you see in your environment to be able to actually drive a self-driving vehicle. All of this was amplified by the fact that we were quickly growing the team. And so a lot of the early intuition that we had learned was hard to translate, and things didn't become as scalable. As a result, we experienced a lot of growing pains. Attempting to replicate the initial success of the founding deep learning team became really difficult. And the symptoms that we experienced were, first, we had a lot of unpredictable timelines. When launching a new project, it was hard to say, this is going to take 6 weeks, this will take 8 weeks. And in a startup environment where your colleagues heavily depend on you shipping your system so that they can test their downstream systems, this became a real challenge. Costs were all over the place. Some projects seemed to land with very reasonable budgets. Others had exploding data labeling and tooling costs, and that was hard to control. And overall, we just had varying success rates. Projects that we thought were difficult sometimes and often succeeded, but other times seemingly very simple projects failed, and that wasn't good. And I think we sort of entered this era that we call deep learning despair, where I think the team lacked a little bit of the confidence it needed to deliver. We were unable to take on new projects which deviated from the current production systems without seeing meaningful regression in key and important areas. And things were hard to predict moving forward. And so from my perspective, trying to outline the technology roadmap, this was unhelpful. So from there, we took a really big step back and we had to ask ourselves, what was the common thread between a lot of our projects? And not to bury the lead here, but a lot of it was focused on data primarily. And so when looking at the successful projects, the first thing was that we saw was that data quality was managed very tightly. The engineers that had spent a significant portion of their time working to ensure that the data sets were consistent and accurately labeled, often we saw a strong correlation with those models performing well. The data also was thoughtfully balanced. Engineers were careful to represent different locations, time of day, weather conditions, and traffic patterns in their data sets, and that generally led to more successful projects. And then, importantly, that the engineers that had a more intuitive understanding of where their networks were failing and the scenarios they were failing in, those were the ones that were successful. And so I think once we started to notice these common themes, we had to ask ourselves, if we're going to apply these learnings across all of our deep learning processes, how do we systematize this as an organization so that we become more successful and we can take on new and better projects? So we adopted what we had called a data-obsessed approach, and we really have 3 key pillars of this. First is what we call our data engine, and this is our system to ingest all of the data coming from our entire fleet of trucks on roads and be able to index that data to make it trivial for developers to access that data and generate diverse data sets. And I'll get into a little bit of what we can do with that later. The second is data quality control. We created a sub-team solely focused on ensuring that the data labels are accurate and consistent. And the third thing was really making it easy to mine new and interesting data and take away a little bit of that human intuition and make that into more of a programmatic experience. So we're starting to automate difficult data mining by implementing active learning systems on our most important models. And so next I want to walk through a little bit of a case study in what it would take for us to generate a new model from scratch. And this model is what we call our Lidar segmentation network. So the overall background here is approximately 8 months ago, we wanted to deploy a next generation Lidar onto our fleet. And the reason for this is in the self-driving industry, the sensing technologies evolve at a very rapid pace. And so you get new sensors that have lasers that can see further, they're more precise, they've got better intensity calibrations. And in general, if we want the most performant system, we've got to be able to adopt these new technologies at a rapid pace. And the goal for this neural network is to assign a class, think road surface, car, truck, lane line, to each laser that we get. And we want to measurably improve our performance of our detection stack by integrating both this new sensor and this new segmentation network. So this is what the rough process looked like from the very beginning all the way through the end. The first is generating an initial data set. So how do we actually collect the data and then train a new model? And then we get into this, what we call feedback loop, on going from making a model, doing the analysis, until it's good enough to be deployed on roads, and that's where that red line is. Then we ship it to our fleet, and then we start to test at a higher scale, and we run a very similar process where we have a very performant model and we do continued learning, but at a much greater scale because it's on more vehicles in the real world. So I first want to dive into what it actually looks like for us to build the initial data set. So collecting and organizing the data. With our fleet of trucks over the last 6 years, we built a very large database of scenarios and conditions that our system has been exposed to, and we've built up this organizational intuition for what's really hard and challenging for our sensors to see and detect, and what's easy. And then using our data engine, we've actually taken all of this data and organized it into a very accessible format, which is indexed by sensor type, region, scenario, and much more. In building the initial data set, the goal is to build a very low effort but sufficiently diverse data set. We shouldn't be spending a ton of time on this data set making sure it's perfect. We just want to get a good baseline to establish the performance and then quickly iterate to understand where we need to cover the gaps. And so in the case of the Lidar segmentation network, what we actually had to do was take this Lidar, put it on a subset of our fleet, and just start collecting data. Collecting data in Northern California, in Oakland here, where there's 8 lanes of traffic on highways and many cars. We take it out to Texas, where you get a lot of humidity, a lot of rain sometimes, but also simpler highways. But we take these trucks and collect data for a couple of weeks, and then we start to organize it so that it becomes way more accessible. So diving into what our data engine now can actually provide us is a number of different queries that we're able to use to actually take this data and create the initial data set. So the basic query parameters that you might be able to expect to do with this data engine, ask for data by sensor type, maybe ask for time of day. Different sensors have different sensitivities to time of day. Location ends up being a really important piece, right? Just driving, 99% of our driving happens 2 lanes in the middle of nowhere, but some of the hardest perception challenges we do face are in the city streets, so we want to make sure that our data sets are focused on some of those challenging problems, and so querying by location ends up being really important for us. And then maybe some of the more complex queries are the more scenario-based ones, and so querying for data around the truck doing lane changes, or maybe a car cutting in really close to us is an important one for us to evaluate the performance of our system on. Or construction zones. Construction zones end up having some of the more complicated perception problems that we need to face as an organization. So what we do here with all of these queries is make, again, that baseline data set. So we pick 10 to 15 different base parameters we want to vary our data across and make sure that we've got a diverse data set across this. And to make this a little bit more concrete, this is actually what an engineer would be faced with to actually make that happen. So on the right, you see the code block of what the query actually looks like. And what this is saying is, get us LiDAR scans from LiDARs identified as 7 and 8 from these 3 trucks captured between September 1st and September 6th, when the truck was traveling at approximately 20 to 25 meters per second, and the truck was traveling through a construction zone. And so as you can see, we're able to be extremely laser focused on the types of queries that we need once we identify that there are problems. So that was the first step, generating the initial data set. Step 2 is to train the model. And I'm not going to go into much of what that looks like today, but essentially we take this model, we run your standard practices for training it, and then we get a prototype. And so we get initial results, and just taking this low effort, low cost approach, you can see we actually get pretty good results just straight up out of that initial process. So you can see on this initial network that we've built that road shoulder and barriers are detected very well. And so in the graphic here, the road shoulders are the dark blue and the barriers are the light blue. But there's some obvious opportunities for improvement. Well, in general, you can see that the network is detecting vehicles in red and the road surface in green. Notably, there's some confusion around the extremes of the output. In the near field, where we've got some confusion between the road surface and the vehicles in terms of the class type. But already we can see that our model is performing very well, which is exciting. So in this case, although it is quite easy to see where some of the failure modes are, in general, when we're talking about building a system that needs to work everywhere all the time, some things are easy to see visually, but other things need to be found programmatically. And that's when we get into more of the analysis piece here. And this is where I think we're doing some really interesting things. And so we've got two types of analysis that we have. So one we call the stratified analysis, and the other is active learning. So on the stratified analysis, what we're doing is characterizing the model performance across all of the diverse areas of interest. And so think back to the scenarios that I was talking about before, understanding the performance of the system while the truck is doing a lane change, or it's doing an emergency braking maneuver, or something's cutting in. Or maybe there's some weather patterns. It's raining really hard, or it's a really sunny day and the sunlight's going right into the Lidar. So we start to segment and understand the performance of our system across all classes, across all of these different scenario types. And you can imagine we've got a graph that describes the performance of our system across all of these different things. And it really empowers our engineers to be able to deeply understand what's working, what's not. If we fix a problem in one area, what does it do to a problem in another area? And that's sort of the game we're trying to play. And really the goal here is to identify the weakest areas for initiating labeling campaigns towards the most problematic areas. And so you can imagine with the queries we're able to make before, given all of these different parameters, get us these data sets that we found on the road so we can send it to scale, get it labeled, bring it back, and train a new model as fast as we possibly can. The second thing that we do on the active learning front is that we automatically identify the difficult data. And so this is really, really interesting. This is where we are not ourselves introspecting into the performance of the model. We're asking the model to tell us where is it performing poorly. And this becomes really powerful because now we've essentially built this automated system where while our trucks are driving on the road, we're able to pull that data, run it through our active learning system, and have the model say, you know what, I was actually confused about these pieces. And so if we look on the bottom right there, you can see two images with some red splotches on them. And really, this example comes from a detection net that we've built, where we've asked it, what are the things that you're confused about? And here it's brought back a couple of examples where we've got this truck towing a trailer of different cars. And it's not something that it's really seen and understood. There's a lot of confusion between, is this the car, is this the truck? All these cars are mounted in weird ways. But what's interesting is the model said, hey, look, this is something I don't understand. And that gave our engineers the opportunity to dive a little bit deeper. And so our active learning system we've applied to a number of different models that we train and continuously improve on. And this has helped us to rapidly iterate, both with the human-in-the-loop process, with stratified analysis and active learning. We're much, much more scientific about understanding the performance of our model in different contexts. And that's really, really important. And then from there, so going back to the life cycle, right, we've built an initial data set, we've built a model, and then we've done a number of different feedback loops to understand the performance of the model. And then we've gotten to a point where we think we can ship it to the rest of the fleet. And of course, there's a number of checks we have to do to get that to work. We have to make our model run in real time, set up sufficient diagnostics, make sure that it's safe and compliant with the standards that our team has before we can send it to be running in production. Oftentimes we'll run it in a background mode before it gets to the real world. But once it's out there, it's live, our trucks are driving on it, then we get into this continuous improvement process. And here we don't expect much, much more improvement in the model overall. Really what we're doing is fine-tuning the system as it experiences and encounters new things that we haven't seen before. And then we're putting that back into our database, make that index integrated into the overall analysis that I talked about before. So here we go from, we've got a performant model, and now we're into sort of this continued learning phase. And then this feedback loop continues essentially indefinitely, right? We collect new models, we collect new data, we try out new models, and then all of a sudden our system gets better incrementally through time, and measurably so. And so, yeah, as I mentioned, the continued learning, we're in the wild, we're evaluating the performance and making it better. And then this is the final result on our segmentation network. And you can see we're getting some very impressive segmentation results. We're very precisely able to understand which lasers are attached to cars, which is attached to the road surface, signs, where is the shoulder. You can even see the lane line markings in cars in the oncoming lane. And so we're able to, with this process, build a very performant model at the end of the day, which is really important. And so what were the high-level takeaways from this? So if we take a step back from where we started, right, when we were in that deep learning despair, we were unable to be confident about building new systems and doing it quickly. We would have varying and mixed results on model performance, and really it wasn't until we took that time to invest in our data strategy to really control the development process and make us more confident and performant as a team. And so the end result was that firstly, we had just much faster time to ship models. It was 8 times faster to ship models in some contexts, starting from scratch. We had smaller and more powerful data sets, and I don't want to understate how important this is. I think, maybe you step back 5-6 years, everything was all about big data. How can you have more data and then just throw really complex models at it to understand? But I think more and more we're converging to how do you have the lightest weight data set that's the most performant? And that's really important because if you're challenging your system with understanding new things and making that generalized, having too much inertia in your model limits your ability to do that. And the last thing that's important to me is controlled and predictable delivery on new systems. And we've got a lot of confidence in our ability to take a new sensor and say we can detect these things in it, and that's really important. And so really those three things that we invested in, our data engine, managing the quality of the data, and then understanding where the failure modes were, took us from a very immature team that had mixed results to where we are today, which is really exciting. And importantly, it scales. So we've got a number of deep learning engineers that are able to use all of these tools every single day to improve our system. So that's all I had to talk through today. Thank you, everybody, and enjoy the rest of the conference.